Good morning, dear students. In this class, we shall take up the plane trusses. Plane truss is a two-dimensional truss. It is a two-dimensional truss. It is a truss structure. It consists of two force members with different orientations. Visualize this figure carefully. This is a two-dimensional truss structure. Two-dimensional truss structure, right? Which has several elements with different orientations. Now we shall see. From here to here, this is one element which has some orientation. This is another element, right? So which is horizontal member. And this is the third element which is vertical in position. This is fourth element, horizontal in position. This is fifth element, inclined in position. If you observe all the elements carefully, all the elements have different orientations. Okay? Next. Here, the members are connected at the ends. At each joint, you see, two or more members joined together. Right? At each joint, if you see, two or more members are joined together at the ends. Right? So, joint we can, understand. We can understand as a point where the ends of two or more members are joined together. Right? Now, see here, each truss member is a two-force member. It undergoes either compression or tension. No truss member undergoes bending. Truss member undergoes either compression or tension. In truss structures, where the forces are applied at the joints only. Forces are applied at the joints only. And where the reactions are applied at the joints only. Remember, here this joint is fixed and this joint is fixed. Therefore, we observe the reactions at the fixed joints. Understand? Now, this truss structure appears as a two-dimensional structure. Okay. Now, where we take nodes at the joints only. Therefore, this is node 1, this is node 2, node 3, node 4, node 5, right? Next, node 6, node 7, node 8. Okay, next. Because it is a two-dimensional domain, at each node we observe 2 degrees of freedom. They are the translations. At node 1, we have a translation like this, which is denoted by capital Q1. At the same node, we have another translation like this, which is capital Q2. Understand? Here, a node is denoted by, say, I. If I denotes a node, right? Q2i minus 1 represents the displacement, horizontal displacement, and Q2i represents the vertical displacement. Horizontal displacement is taken to the right and vertical displacement is taken, horizontal displacement is taken to the right and vertical displacement is taken upward, right, at the node I, where Q2i minus 1 and Q2i are the displacements at the node, are the rectangular displacements at the node I. Okay, this convention we form. Put I equal to 1. Then what you get? Q1, Q2. When you put I equal to 2, then this becomes Q3, this becomes Q4. So when I equals to 2, you get displacement Q3 and displacement Q4 like this. Okay. Now here, this truss, is representing a domain. Any point in this domain is specified by two coordinates, x and y. Therefore, you want a global reference frame with coordinate axis x and y. How you take? I can take the coordinate axis x rightward like this with origin here, and vertical axis vertically upward. This is the reason why the displacements in the direction of x I consider positive, and the displacements in the direction of y I consider positive. Okay. The displacements in the positive direction of x I consider positive, and the displacements in the positive direction of y axis I consider positive. Okay. Now here the loads P1, P2 and P3, they are vertically acting downward. Therefore, with respect to this reference frame OXY, they are considered negative. The vertical force acting downward, I consider negative, and the forces acting vertically upward, I consider positive. Okay, next. Now, I take a truss member. Truss member, if you observe, truss member consists of same cross-sectional area. Each truss member has same cross-sectional area, has uniform cross-sectional area, right? The truss member may be, subjected to, two equal, opposite and collinear forces like this. Then it undergoes elongation, or the truss member may be subjected to two equal, opposite and collinear forces as shown. Then it undergoes compression. Here the forces are collinear in action, their magnitudes are same and directions are same. Here also the forces are collinear in action, magnitudes are same and directions are opposite. In this case, member undergoes compression, and in this case, member undergoes tension. Right? Truss element may undergo compression or tension. Truss element is a two-force member. Right? As I said, to define the entire truss, we take global coordinate system, whereas for an element, we take a local coordinate system. The reason is, the elements of the truss have different orientations. Therefore, to account for these orientations, we take both local and global coordinate systems. The local coordinate systems we take for the elements of the truss, and the global coordinate system we take the entire truss. Right? Next. Here, I have a truss element with the orientation shown. So what is the orientation here? Observe carefully. This element has the orientation which is noted by theta. For the entire truss, I take a global reference frame OXY, whereas for each truss element I take a local reference frame. Now for the truss element considered, x dash is the coordinate axis with coordinate origin here, say 1. Okay. Now this is the node 1 and this is the node 2. Okay. This truss element may undergo compression or tension under the action of several forces acting at the joints of the truss. The forces acting at the joints of the truss produce either compression or tension in the truss element. Right? Therefore, I say the node 1 displaces by an amount, say Q1 dash, and node 2 displaces by the amount, I say Q2 dash. Now how this looks? If you observe this element, it is looking like a one-dimensional element. One-dimensional element. Two-noded bar element. We know the two-noded bar element connects two nodes, say 1 and 2. Right? Each node has only 1 degree of freedom, like this. This is what we have learned. Okay. Right? How this element is behaving, this is also behaving. Okay. With respect to this reference frame, I can define Q1 dash and Q2 dash are the nodal displacements of the element. Understand? But if you observe, the entire truss, the node 1 has how many displacements? 2 displacements. The node 1 has 2 displacements, Q1 and Q2. These are the global displacements, Q1, Q2. They are the global displacements of node 1. Q3 and Q4, they are the global displacements of node 1. Because truss structure is here a 2-dimensional truss structure. Each node consists of 2 degrees of freedom. And when you take the whole domain into consideration, but when you take each truss element as a subdomain, as a finite element, okay, as a finite element, the behavior of the truss element, right, looks like the behavior of a two-noded bar element with respect to the local reference. Okay. Now, in fact, with respect to the global reference frame, this node 1 displaces by an amount, say Q1, horizontal, right? And the same displaces by an amount vertically by Q2. That is what is shown here. The node 1 is displaced by an amount Q1 and node 1 is displaced by an amount Q2 vertically upward, because each node has 2 translations. This is the horizontal translation, this is the vertical translation. Node 1 displaces by an amount Q1 horizontally and the same node displaces by an amount Q2 vertical, like this, upward, Q2. Hence, the resultant of Q1 and Q2, the resultant of Q1 and Q2 I determine. That I say Q1 dash, we see, Q1 dash, okay, how we determine Q1 dash? Here Q1 dash is the resultant of displacements Q1 and Q2, where displacement is a vector, it is not scalar, therefore you have to consider direction also in addition to magnitude. How I determine Q1 dash, that I tell you here. Theta is the orientation of the truss element and Q1 is the displacement of node 1 in the direction of x-axis, capital X. Next, Q2 is the displacement of the same node in the direction of y-axis. Okay. Now what is my interest to determine their resultant? I say their resultant is Q1 dash. How you get? This is theta. From this point, draw a line perpendicular to the truss element. This is 90 degrees. Okay? Because this is Q1, if you observe this triangle, it is a right angle triangle. Now what is this side? This equals to Q1 cos theta I have here. Okay? Next. Now, if you observe here carefully, this side. How you get this side? It is simply Q2 sin theta. From here to here it is Q2 sin theta. Understand? Therefore, Q1 dash is Q1 cos theta plus Q2 sin theta. That is what I have written here. Next. Now, displacement of 2 in the direction of x dash I want. That is Q2 dash. How you get Q2 dash? It results from the vector sum of Q3 and Q4. What are Q3 and Q4? Q3 is the horizontal displacement of node 2 and Q4 is the vertical displacement of node 2. With respect to the assumed reference frame, I am taking the directions. Right? Again, this is theta. Now, from this point, draw a line perpendicular to the length of the element. Okay? This is a right angle triangle. Therefore, this side can you determine? Yes, this side is simply Q3 cos theta. Right? Now, this is Q4. Right? And how you get this? This is simply Q4 sin theta. Hence, I define Q2 dash as Q3 cos theta plus Q4 sin theta, where theta is the orientation of the truss element. Okay, once you determine Q1 dash and Q2 dash, right? So can you develop the element stiffness matrix? Yes, because we have Q1 dash, this is the truss element, this is node 1 and this is node 2, we have Q1 dash and we have Q2 dash. How it looks with respect to local reference frame x dash, this is local reference frame x dash. How it looks like this element, a two-noded bar. Therefore, the concept of this two-noded bar element we are applying here to the truss element and derive the element stiffness matrix. Okay? Now we have two equations, right? We can represent in matrix form also. We can represent in matrix form also. Right? Okay. Let us see. How you represent in matrix form? Before you represent in matrix form, define the element displacement vector in terms of the nodal displacements defined with respect to local reference frame. The element displacement vector here is denoted by Q dash, which is a column matrix having the elements Q1 dash and Q2 dash. With respect to the local reference frame, here the behavior of the truss element with respect to local reference frame is same as the behavior of a two-noded bar element. Very simple. The behavior of the truss element with respect to local reference frame x dash is similar to the behavior of a two-noded bar element. What are the nodal displacements here? Q1 dash and Q2 dash. Therefore, we define the element displacement vector Q dash is a column matrix having the elements Q1 dash and Q2 dash. Okay. Now, I told you how you represent, the global displacements and the local displacements. If you take J as the node, Ri as the node, doesn't matter, you take J, Ri. If you take J as the node, right? So Q2J minus 1 is the horizontal displacement and Q2J is the vertical displacement. If you take I as the node, doesn't matter, Q1 2i minus 1 is the horizontal displacement and q2i is the vertical displacement. These are the notations which we follow for global displacements, and the same convention we can also follow for local displacements, right? Okay. Now, this is the element displacement vector. This is the element displacement vector, which is a column matrix. Understand? With respect to local reference frame. But with respect to global reference frame of the same element, how you define the element displacement vector, that is the question. I take the same element with same orientation theta. This is node 1 and this is node 2. Node 1 has the horizontal displacement q1 and the same node has the vertical displacement q2. At node 3 this is the direction of q3 and this is the direction of q4. These are the nodal displacements defined with respect to global reference frame OXY. OXY, remember, OXY, right? Therefore, with respect to the global reference frame, can you define the element displacement matrix Q? Yes, it is a column matrix having elements Q1, Q2, Q3 and Q4. Why you determine? Ultimately, the local displacements are the nodal displacements with respect to local reference frame. You have to convert into the nodal displacements with respect to the global reference frame OXY. Okay, now? We had Q1 dash equals to Q1 cos theta plus Q2 sin theta. We know it. We already derived. And similarly, Q2 dash equals to Q3 cos theta plus Q4 sin theta. Where? Understand here carefully, Q2 sin theta, how you write this, sin theta is simply cos of 90 minus theta, then you get sin theta, right? Similarly, here, how you write the sin theta cos of 90 minus theta, understand, careful. So both equations, if you express in matrix form, how you get? The first equation is Q1 dash, which equals to Q1 cos theta plus Q2 sin theta. The second equation is Q2 dash equals to, as we have, Q1 cos theta plus Q4 sin theta. Understand? These two equations you can represent in matrix form. How you represent, I write a column matrix like this, having the elements Q1 dash, Q2 dash, into, right? A matrix with unknown size like this, into a column matrix having the elements Q1, Q2, Q3, Q4. I write like this. Take first equation. Q1 dash equals Q1 cos theta plus Q2 sin theta. So cos theta I write here. Right? Next sin theta I write here. Next 0, 0 I write here. Second equation you take. I put 0 here, 0 here. Then cos theta here. Then sin theta here. Okay. Sin theta is cos 90 minus theta. Okay. So this matrix I denote by L. What is L? Here L is the transformation matrix. This matrix Q1 dash and Q2 dash. Here the matrix containing Q1 dash and Q2 dash. I denote this by Q dash. So Q dash equals to, the transformation matrix L into the matrix Q. What is Q dash? I told you, element displacement vector defined with respect to local reference frame. And what is Q? Element displacement vector defined with respect to global reference frame. Where L is the transformation matrix. What are L and M? They are the direction cosines. L is cos theta and M is sin theta. Understand? Using this expression, you can transform the local nodal displacements into global nodal displacements. Or using this expression, you can transform the displacements of the nodes defined with respect to local reference frame into the displacements of the nodes defined with respect to global reference frame. Understand? Okay? So what we have learned in this particular class, we have taken a truss structure and we understood how it behaves. We know that truss structure consists of several elements. Each element has different orientation. Forces are applied at the joints. Under the action of the forces acting at the joints, each truss member undergoes either compression or tension. No bending occurs. Node is considered at the joint. Each node in the plane of truss has 2 degrees of freedom, right? And each truss element with respect to its own reference frame consists of 2 degrees of freedom with 1 degree of freedom at each node, right? We derive the expressions to determine the nodal displacements with respect to local reference frame, and they are transferred to the nodal displacements with respect to global reference frame, right? And from them a transformation matrix is derived which consists of the direction cosines. The transformation matrix is dependent on the values of direction cosines. Okay, thank you.